These passes could be extended to passes which have more lengths, which have bigger lengths. Okay, but these passes could not be extended. For example, in these passes, we terminate at a final node, and as you know, final node have no existence edge and could not be extended. And when we try to extend these passes, which is terminates at a non-final node, if we try to extend this path, for example this path, we should go ahead to node 5 again, and we know that we have visited node 5 in this path previously, so we have a loop on our path. So this is not be a simple path, and the definition of simple path is violated by this loop. So this node could be extended to other simple passes. Okay. Then go ahead with passes of length 4. We have 3 passes of length 4. All of them are terminated passes, so none of them could be extended to passes with bigger lengths. Okay. This is the process of detecting all simple passes. How we detect, how we extract prime passes. As you know, prime pass is a subset of these passes, because a prime pass is a specific simple pass which could not be subpass of another simple pass. So these all passes of length 4 could be a prime pass, because none of these simple passes could be a subpass of others. Okay, none of these could be a subpass of the others. This said, none of these passes could not be a subpass of these passes with smaller lengths. It's trivial. And on the other hand, none of these passes could be a subpass of these other two passes. Okay, so this said, these 3 test passes, these 3 simple passes are prime passes. So to define prime passes, we told you why these are prime, and we go ahead, we come back to simple passes with smaller lenses. In the simple pass with smaller lenses, we reach to length 3. From length 4, we reach to length 3. And if you check these final test passes, these non-terminated test passes could be executed, could be extended by these test passes, and these test passes, these simple passes, are sub passes of some of these simple passes. But in this set, if we check, we see some of them specifically, especially these three passes which start by a non-initial node, could be subsumed, could be sub-passes of some of these test passes. 2, 3, 4, 7. 2, 3, 4, 7 is a sub-pass of this pass. So this could not be a prime pass. But those of them which started by an initial node and terminated at a final node, or at a terminated node in a loop which could not be extended, so these are prime pass. These are prime passes of length 3. We go ahead with passes of length 2. As I told you, these passes which are not marked by any of these symbols could not be a prime pass because they are extensible. They could be extended by passes with bigger lenses. Okay, but among other test passes, some of them could be covered by test passes with bigger lenses, such as 3, 4, 7, 3, 4, 7. Okay, or 3, 5, 7, 3, 5, 7 is a subpass of this test pass. Or 3, 5, 6 is a subpass of this pass. But none of these test passes, these simple passes, could not be covered by any other prime passes, any other detected prime passes. So they are marked as prime pass of length 2, which tries to test our loop, which started with any node located in our loop. Okay. To cover these prime passes, we should define some test passes that they can cover them. How we define test passes in order to cover all of these prime passes? We want to cover all of these prime passes by fewer test passes. We try to have fewer test passes. So we defined a new notion as a round trip. What's a round trip pass? A round trip pass is a prime pass that starts and ends at the same node. Round trip pass. We want to define passes to cover some of our prime passes, such as these passes. Okay, so these passes start from a node and ends again at that node, this one and this one. So we define round trip as a prime pass that starts and ends at the same node. Round trip. Simple round trip coverage criteria is defined as this definition. All test requirements contains at least one round trip path for each reachable node. If we can define a cycle by a reachable node, we should define a round trip path. For example, in this graph, we could define a cycle for this node and for this one. So we have to define two round trip paths, at least two round trip paths. Okay. Test requirement in this coverage criteria contains at least one round trip path for each reachable node. In graph G, that begins and ends a round trip path. Complete round trip path coverage criteria is defined, which subsumes simple round trip path coverage criteria. In this coverage criteria, we define test requirements as all round trip passes for each reachable node. All round trip passes for each reachable node. In this simple round trip coverage, we need to have at least one round trip path. But in this complete round trip path, we should have all round trip passes in our test requirements. So it's trivial that this coverage criteria subsumes this one. This criteria omit nodes and edges that are not in round trip path. Please check this item for this definition later. How this item could be true with respect to these definitions. They do not subsume edge pairs, edge or node coverage. Why? Why these coverage criteria don't subsume edge pair, edge or node coverage criteria? Why? Because when we talk about round trip, we just talk about the loops and not other nodes of our graph. When we define our coverage criteria as node coverage, we should cover all nodes of graph, not nodes just located in our loops. The round trip coverage criteria in both forms, simple form or complete form, talks about loops, about cycles. So they are not subsumed, they could not subsume edge pair, edge or node coverage criteria. These coverage criteria are defined just for handling loops. Okay. This is the final slide. Is defined in this set for structural coverage criteria. So we have several coverage criteria for structural coverage criteria. We start with edge coverage, node coverage, and go ahead with edge pair coverage. We have defined prime pass coverage. We have defined complete pass coverage. We defined simple round trip coverage and complete round trip coverage. These are all coverage criteria which are defined for structural coverage criteria. We turned on to another notion as data flow criteria. In data flow, the goal of checking data flow criteria is to ensure that values or any variable are computed and used correctly. So in this coverage criteria, we focus on when and how our values for our variables are computed and when they are used and how they are used. Are they used correctly, or are they computed or defined correctly? It's important in software testing. So we define some other coverage criteria for data flow according to data flow graph. Probably you are familiar with data flow graph in compiler course in your bachelor study. Two notions are important in this criteria, these types of criteria, are definition and use. Each variable in our program could be defined and then could be used. Could be defined in some statement of our program and then could be used in later statements of our program. Okay. So a location where a value for a variable is stored in memory could be defined as def location. This location could be any node of our control flow graph or any edge of our control flow. So a location where a value for a variable is stored in memory could be defined as a def location. Okay. And on the other hand, we have use location. A location where a variable's value is accessed. When a variable's value is read, or when it contributes in computation some other variables. For example, in a typical program, suppose we have this control flow graph. In this control flow graph, suppose that we defined the value of x variable at this location, and then we use it in these two locations. In this location, we use value x to compute the value of z, And this location, again, we use x in another way to compute the value of this variable. Okay, so there are two uses for this definition. This is a definition location for x, and these are two locations in which we use this variable. Okay, so look at this box, and we want to fill these sets. The def locations for the def variables in location 1 is just x, and the def location in 5, the def location 5 defines just z, and in location 6 we also define z. Okay, uses in this location is just x. In this location we just use x variable. So user 5 is a set in which we have only one variable, and this is the same for the next one. Okay, in location 6 we have used just this variable. Okay, the values given in defs should reach at least one, some or all possible uses. Please note to this piece of sentence. The values given in defs, should be reached at least one, some or more possible uses. According to these three options, we could define three different coverage criteria. Let me go ahead. We define du pairs and du passes accordingly. Def n or def e defines the set of variables that are defined by node n or by edge e. Def n, as you saw in this example, def 1 is the set of all variables defined in location 1, in node 1. Def 5 is a set of all variables that are defined in node 5. This is true for all nodes. This could be defined for all edges. For any edge of our control flow graph, we could have some variables to be defined. Okay, so we define def e in the same manner as the set of variables that are defined by edge e. And in the same way, we can define use n and use e. The use n is the set of variables that are used by node n, and the use e is the set of variables that are used by edge e. According to these definitions, we define du pair. What's a du pair? A pair of locations Li and Lj such that a variable v is defined at Li, location I, and then used at location J. So Y and 5 could be a DU pair, def use pair, a pair of definition and then it's used. And 1 and 6 could be a DU pair because a variable is defined in location 1 and then it's used in location 6. So this could define a DU pair. So a DU pair is defined as a pair of locations Li and Lj such that a variable v is defined at location I and then it's used in location Lj. A def clear path is defined as a path from location I to location J with respect to a variable v if E is not given another value on any of the nodes or edges in the path. Suppose we have this control flow graph. This could be a def clear path. Def clear path for this DU pair because in intermediate nodes there are no other definitions for the variable x. The variable x is just defined at location 1 and there are no any other definition for x along the path until we use it. So this is a def clear path. And so with this one is also a def clear path 1, 2, 4, 5 because there are no any other definitions for x in these two intermediate nodes or in this edge. Okay, so this is a def clear path. Okay, we define this notion again. A path from location I to location J is a def clear with respect to a variable v if v is not given another value on any of the nodes or edges in the path. The next notion is reach. What's the definition of reach? If there is a def clear path from location I to location J with respect to some variable v, the def of v at location I reached the use at location J. For example, in previous control flow graph, this definition reaches this use and this one. These two uses locations are reachable from this definition. These two uses locations, location node 5 and location node 6, both of them are reachable from this definition node. So location 5 is reached from x and so on with location 6. The next notion is DU path. DU path is a simple subpath that is def clear with respect v from a def of v to a use of v. I explained this notion when I talked about def clear. And du ni to nj with respect to variable v defines the set of all du passes from ni to nj. For example, in previous control flow graph, du passes from location I to location 6 have two passes. The first one is this pass and the second one is this one. And this du pair 1 and 5 have again two passes, this pass and this pass. These passes are subpasses, or simple subpasses that is def clear with respect to v, from a definition node to a use node. Okay, set of all du passes from ni to nj. Du ni and v defines the set of all du passes that starts at node I. For this last one, we have four du passes. Suppose we have one definition, but we have two uses. So for the last notion, we have four passes. One of them is this one of them is this one. These are two passes that connect node 1 to node 6, and we have two other passes that connect node 1 to node 5, because the 1 to all uses of x is defined by these four passes, as I explained before. Du ni with respect to variable v, the set of all du passes that start at ni. Okay, we define Turing du passes. A test pass P du tours subpasses D with respect to variable V if P tours D and the subpass taken is def clear with respect to V. As you know, a test pass should be started at initial node, and it should end at a final node. And a test pass, when a test pass tours some du pass, we say that the test pass du tours that du passes. Okay, I will explain this notion by an example in later slides. And we could have side trip again for covering all du pairs. Some of du pairs, some of uses are located in loops, and we have to use side trip and detours to cover them. The time is over. A mid-course exam could be usable, could be very valuable. If you want, we could have a mid-course exam. no problem. If you want, we can take an exam next week. No problem. It could be very valuable. You could be familiar with our testing, with our questions in your final. If you are agree with this suggestion, we can take an exam next week. Okay, let me go ahead. According to our talks, we could have three types of criteria for covering DU pairs. Use every definition, get every use once, or follow all DU passes. Could be three types of our coverage criteria that formally defined in later slides. All div coverage, let me see, excuse me, the time is over. Let me explain this coverage criteria in next session. Please ask your questions if you have any question. This time I have no problem with this time. No problem. You can be ready for this time and I take an exam. Okay. Please ask your questions. No question. How about your representation? Your research, your study research. You should sessions for your presentations. If you can ready for next week, you can start your presentation, and I hope all of you be ready. The exam in this time because okay, I will take an exam from chapter 1 to chapter 7, except chapter 4. We have omitted the chapter 4. Just the chapter 4 is being omitted in our lectures. No, I will finish chapter 7 next session, and you should be ready for that time. Let me see your results and I decide about marks. If you are good in your exam, we consider more mark, and else we consider less. Okay, if you have no question, it's too much. You should be ready for your final exam.